So this is Unit 1, Lesson 6 for the AP Calculus course. The unit is called Limits and Continuity. The lesson is called Algebraic Properties of Limits. What we're going to learn in this lesson is when we can directly substitute the limit value into a function to find the limit. We're going to learn some basic ways to use algebra to rewrite functions so that we can use this direct substitution method. And we're going to learn about when we find limits, what's the difference between undefined versus indeterminate? Let's look at some examples. So, direct substitution. When we say using direct substitution to find a limit, we're saying this right here. If f of x is some polynomial or rational function or any real continuous function, and a is in the domain of f of x, then the limit as x approaches a of f of x is equal to just f of a, so just evaluating at that point a. So if we look at our two examples here, we have a quadratic, which is definitely continuous polynomial, and we have a sine function, which we know is just a continuous wave. So for these functions, we can just use direct substitution for f of 4 and f of pi respectively to find the limits for each of these. So the limit as x approaches 4 of x squared minus 5x plus 4. To find that limit, we can just evaluate at f of 4. So 4 squared minus 5 times 4 plus 4. And some calculations will yield that f of 4 is equal to 0, which tells us that the limit as x approaches 4 of this function is equal to 0. The next example, the limit as x approaches pi of sine of x. Now, we'll use what we know about trig here. We can kind of sketch a graph of what sine of x looks like. So sine of 0 is 0, and sine of pi over 2 goes up to 1, and then sine of pi goes back to 0, sine of 3 pi over 2 goes to negative 1, and sine of 2 pi will go back to 0, and we just repeat this wave as we continue in intervals of pi over 2 in either direction. So if we use direct substitution, we could find the limit as x approaches pi of sine of x by finding sine of pi. So as we can see from our sketch of our graph, sine of pi is 0. So we can conclude that the limit as x approaches pi of sine of x is also equal to 0. What does this look like graphically? So here's our two functions we just looked at. If we look at the first one, as x approaches 4, we see that this is definitely continuous. There's no holes in this graph. The left and the right are always going to be equal to each other. So we just find f of 4 is 0, and we can find the limit there really easily is equal to the value of f of 4. If we look at our sine of x function, we can find x equals pi. And we see that f of pi is equal to 0, which is consistent with the limit as x approaches pi from the left and from the right, both limits equal 0. So now, what happens when we use direct substitution and we get an answer that we're going to call undefined? So if I use direct substitution on either of these examples, so the limit as x approaches 1, if I plug in 1 for x, I get x equals 1 on top, and then the natural log of x becomes the natural log of 1, and the natural log of 1 equals 0. So if I remember, that means that e to the power of 0 is equal to 1. That's how I remember natural logs. And so what we get here is if we use direct substitution, we get the answer 1 over 0. And so this does not tell us that the limit is 1 over 0, but this answer at x equals 1 tells us that the limit as x approaches 1 is undefined. And the big thing here is that the denominator is equal to 0 with direct substitution. Similarly, for the second example, if we try using direct substitution, we get a denominator that is equal to 0 The numerator is 3. So this is also going to be undefined. If we look at undefined for these examples on a graph, we're going to see for y as x approaches 1, we get this, basically we get a vertical asymptote. And we see that from the left, as x approaches 1, our function goes to negative infinity. And as x approaches 1 from the right, we go to positive infinity. So we can definitely see that in this case, undefined means that the limit does not exist. So if our direct substitution gives us an undefined answer, the limit does not exist. We can call it undefined in this case. We can look at the same analysis for our second example as x approaches negative 4. For our other function, we see we also have a vertical asymptote. As we approach x equals negative 4 from the left, negative infinity, from the right, positive infinity. So that's what that looks like. That's what undefined looks like on a graph. So sometimes direct substitution can give us an answer that it just fails. So if we end up with, so we got 3 examples here. If we use direct substitution on each of them, we find an answer of 0 over 0. And that's different than before, because before we get some number that's not 0 over 0. So 1 over 0, 3 over 0. But now, in both of these, all 3 of these cases, direct substitution leaves us with 0 over 0. And so this is not undefined. This is called indeterminate. And what indeterminate tells us is absolutely nothing. Indeterminate tells us that there are still an infinite number of possibilities for the limit. The limit could be defined at a certain value, or the limit maybe doesn't exist. We don't know. Direct substitution gives us no information about the limit for these examples. And so we can still use some algebraic rules to find the limits for these problems, but direct substitution is not going to be the method we use. In the next lesson, we'll look at each of these examples and figure out how to find the limits, but that's for the next lesson. And we can skip the graph for these ones. Takeaways. So this lesson, hopefully we built some more confidence with looking at the functions in kind of algebraic notation and how to find the limits. What does it look like when a limit is undefined or when there's a vertical asymptote? And what does it look like to get an indeterminate answer using direct substitution? And so undefined and indeterminate, we're going to call our D words, which is just a Jansen's ism. Doesn't really mean anything anywhere else.